Hello, everyone. In this lecture, we're going to look at an example of logistic regression. So that is logistic regression. We're going to have a step-by-step guide about how to do the logistic regression and through this example, okay? So studies have shown that various aspects of a server's appearance have an effect on tipping. A group of researchers decided to see if the color of clothing a server wears has an effect on the tipping behavior. Okay, this experiment involves 418 customers. The response variable is Y, is whether or not the customer left a tip. And the explanatory variable X is whether the server wear a red top or not. So X equals to 1 if the server wear the red top, 0 if the server wear a different color top. The server in this study wear a red top for 69 of the customers, wear different color top for 349. So 69 plus 349. So in total, we actually involved 418 customers. The probability that a randomly chosen customer will tip have two values, P1. You see here, P1 for those who wear red top and P0 for those who wear a different color top. For this study, 40 out of 69, the tip a server, okay, who wear red. 130 out of 349 customers tip server when wearing a different color. So here, X equals to 1. So what's the estimate of P1? So we want to estimate the probability that the customer will tip for those who wear red or for those who wear a different color. So X equals to 1. The server wear red. X equals to 0. Server wears other color. Other colors. So what is P? What is P1 hat? And what is the P0 hat? So P1 is the probability a customer, a random chosen customer will tip for those who wear red. This is actually equals to, so how many? 40 out of 69, right? This is 130 out of 349. So 40 over 69. This is 130 out of 349. If we do the calculation, this one will equals to 0.5797. This one equals to 0.3725. Okay. So now we have the estimated probability. Now the odds, what is the odds? The odds is a ratio of the proportions for two possible outcomes. Okay. So what is the odds for a customer tipping when the server wear red? So we want to have the odds red. So this should be tipping. So this should be P1 hat over 1 minus P1 hat, right? So based on the definition, so this will equals to, this is 0.5797 over 1 minus 0.5797. This equals to 1.3793. Then what is log odds? Log odds is log P1 hat over 1 minus P1 hat. So equals to log 1.3793. This will equals to 0.3216. Okay, now what is the odds of a customer tipping when the server does not wear red? So odds other color. This will equals to P0 hat over 1 minus P0 hat. This equals to 0.3725 over 1 minus 0.3725. This equals to 0.5936. Then what is a log? So let's take the log P0, 1 minus P0 hat. So this will equals to log 0.5936. So this equals to minus 0.5215. So now we have X, we have probability people will tip, right? A customer will tip when the server will red, and the probability that this is the probability when the customer tipping when the server will red. This is the probability customer tipping when the server does not wear red. And then based on this probability, we calculate the odds, the probability of tipping, probably not tipping when the server wear red, right? Odds is probability of success divided by probability of failure. So here is a ratio between customer tipping and customer not tipping. Now, why do we need to convert the customer tipping into the probability? Now let's have a look at the what is the range of probability? The range of a probability always belongs to 0 and 1. Yeah, that's a probability. You can get 1, so it should be this way. Then what is the probability of P? This is the odds, 1 minus P. This actually belongs to, so when P equals to 0, and you actually got 0, right? 0. When P equals to 1, this goes to infinity. So how about log odds? Log P 1 minus P. This belongs to, when P equals to 0, when this odds is 0, so it should goes to minus infinity, and then plus infinity. So those are the range. So now if we look at the range of probability P and odds, so this is the odds, this is the log odds. So why do we need to do a transform from P to odds to log odds for logistic regression? So in simple linear regression, we model the response variable. For example, the response variable y equals to beta 0 plus beta 1 x plus epsilon. You see the x range is pretty big. When x belongs to minus infinity to plus infinity, then y also belongs to minus infinity to plus infinity. So if we have this y, and we cannot just model the probability as the y. So that's why for the probability in classification problems, y only take two values. For example, in this case, y is customer tipping or not. So that's 0 and 1. So the mean is actually the probability of a success, the expectation. So simple logistic regression model P, and if we try to model P as a function, for example, you can model P equals to beta 0 plus beta 1 x. This won't work because beta 0 and beta 1, if anytime the beta 0 and beta 1 is greater than 1, then you will cause the probability to be greater than 1. Okay, and you cannot use log odds, because log odds, if you do P1 minus P equals to beta 0 plus beta 1 x, this is also wrong because this one is in the range of 0 to infinity. So a perfect way to do the classification model and model the probability of success is you use log odds, log P 1 minus P, and equals to beta 0 plus beta 1 x. And this is right. This is because in the classification problem, we have a 0-1 binary classification. And if we want to model the probability to get a particular outcome, right? So we have to convert it into the log odds. So that's why we study the range and the transformation of response that we make, so that we can have a formulation to model the probability you get a binary outcome. So this is not a good model, not a good model, not a good model, not a good model. This is a good model. So now let's have a look at maybe let's plot. Let me create a plot here. Let's see if you have probability here. This is probability 0, and this is probability 1. Maybe 1, and you have 0.1. Is it 0.1? 0.5. Let's fix 0.5 first, and 0.2, 0.3, 0.4, 0.5, and then 1, 0.6, 7, 8, 9, and 10. Now this will be the value, okay, of for example P over 1 minus P. So if you have a probability in this range, what is P 1 minus P? How to draw this figure? I think we know that if P equals to 0, this P1 minus P is 0. We need to find another value because this goes to infinity. Let's find 0.5. If P equals to 0.5, P equals to 0.5, P1 minus P equals to 1. So let's find, maybe this is 1, 2, 3, 4. Now I think I have this point, so this will be the curve. We go outside of 1, so no, because because P is always less than 1, right? So let's draw a boundary here. Draw a boundary here. Then when P equals to 1, it will goes to infinity. Okay, so this is it goes to infinity. So this is a curve of P1 minus P. Now what is log 1 minus P1 minus P? This is the curve P1 minus P. Then what is the curve? What is the curve of log? Log P1 minus P. Log P1 minus P. Log P1 minus P. We need to find two values, because if P equals to 0, then log P1 minus P will equals to minus infinity. So this will goes to here, and then like this. So this curve will be log P1 minus P. Okay. Because when P here, when P equals to 0.5, log P1 minus P will equals to 0, because this is 1, right? Log 1 equals to 0. Now we have two curves. Let me differentiate them. The second curve, this is a log P1 minus P. And this is log P1 minus P. And this is odds. This is a log odds. This is a log odds. Okay, now we know why we want to do this log odds when we do the logistic regression. Because we want our response variable to be in the range of minus infinity to infinity. Okay, then we can model the linear relationship. Now it comes to the next step. The statistic model for simple logistic regression is log P divided by 1 minus P log odds equals to beta 0 plus beta 1x, where P is the binomial portion and x is the explanatory variable. So in this case, x equals to 1, x equals to 1, x equals to 0, and what is P1? What is P? P1 actually equals to let's see, P1 0.5797, 0.5797, and P0 is I think it's 0.3725, and then we got P1 hat over 1 minus P1 hat. This equals to, maybe let me save some space. Now the odds is P1 hat over 1 minus P1 hat. This equals to 1.3793. And P0 hat 1 minus P0 hat equals to 0.57, the 0.5, no, let me see, 0.5936, 0.5936. And then we got our log odds. So log P1 over 1 minus P1 hat equals to 0.3216. Log P0 hat 1 minus P0 hat equals to minus 0.5215. Okay, now in the tipping example, there are totally 418 observations. The explanatory variable is whether the server wear a red top or not. So it's right here, or not. Now, which is coded with the indicator x equals to 1 or x equals to 0. Okay, for server wearing a different color. Please write down the model for server wearing red. So this will be log p1 over 1 minus p1. Okay, this equals to beta 0 plus beta 1 x. But x equals to 1, right, for red. So this will equals to beta 0 plus beta 1. And this actually equals to this value, 0.3216. How about the model for log p0 hat over 1 minus p0 hat equals to beta 0 plus beta 1x equals to beta 0 plus beta 1 times 0. Because different color, we use the indicator function x equals to 0. So this equals to beta 0 equals to minus 0.5215, because it's right here. Now we know beta 0 equals to this one, then beta 0 plus beta 1 equals to this one. So beta 1 equals to 0.3216 minus beta 0. So equals to 0.3216 plus 0.5215. This will equals to 0.8431. So now you can find the estimation. Now we have already found the estimation. Beta 0 hat is equals to minus 0.5215. Beta 1 hat equals to 0.8431. Okay, now the equation will be log. We have the odds. This will equals to log p1 minus p equals to we don't have enough space here, but it's actually equals to minus 0.5215 plus 0.8431x. So this is our equation. Now, what is the ratio of the odds when people wear red? So odds red. What's the ratio of the odds wearing red and odds when people wearing a different color? Odds other. This is actually equals to, let's go back and have a look at the value odds red. What is the odds red? It's right here. So this should be 1.3793. 1.3793 divided by 0.5936. 0.5936. This equals to 2.324. And the odds red, if we use this equation, how do we calculate that? So this will equals to odds red log odds red will equals to minus 0.5215 plus 0.8431. Because you have an x here, but x equals to 1 when it is red, right? And log, if you have log odds other color, this will equals to minus 0.5215. Now, if we do the log odds red divided by odds other, this is actually minus, right? This is actually equals to log odds red minus log odds other. So in this case, we will have equals to 0.8431. And so this is also equals to exponential 0.8431, because this is log. You take exponential on both sides, you will get this will equals to odds red over odds other. Okay. Now, two different ways that you can, once you get the equation, you can also do it. Now, what will happen? So the odds, so what does this mean? The odds red over odds other is about 2.3 times. A server where red, the odds of tipping when a server wear red is about 2.3 times the odds when a server wears a different color. Notice that we have chosen the coding, right? The coding is x equals to 1 is red, x equals to 0 is other color. Here, for illustration purpose, we use discrete value of x, but in the real world, all the explanatory predictors, they could be all real numbers. But the classification outcome is always 0 and 1, and we are trying to model the odds and the log odds. What will happen if we code, if we switch the coding, what's going to happen for a server wearing a different color? Now we're going to change this. We're going to switch back to red is x equals to 0, and then other is x equals to 1. So now if we redo this formulation, what's going to happen? Okay, now previous one, when we do this model, okay, when we choose the indicator so that the regression, you see the slope, we have an intercept. This is an intercept. This is the slope. The slope is actually positive, and this will give the odds ratio greater than 1. If we code it in different ways, the fitted equation, if you try to if you redo it, the log odds will equals to 0.3216 minus 0.8431x, and the odds ratio, the odds red over odds other. What will be the odds? Odds red over, so x is red, x 0, right? So this will be the new equation, and we can see the log odds. Let's get the log odds. We can do the log odds. Log odds red will equals to 0.3216, because now we're coding our red as this one, and the log odds other will equals to 0.3216 minus 0.8431, and log odds, now we use log odds minus log. So odds red will still equals to exponential 8431. Okay. It doesn't change the results because if you see if we are going to get log odds red over odds other, this is actually equals to log odds red minus log odds other. And this actually, we have values here. This equals to 8431. And then that's why we got this. It doesn't change the result. It's just a way of coding and how you code them in different ways. If you flip the coin, if you try to say, oh, what is the odds other over odds red, this will equals to exponential minus 0.8431. This actually equals to 0.43. So if you divide by 1, this is actually equals to 1 over 2.324. So the coding doesn't actually change the this odds ratio, and only change the models, and I mean switch the model to a different way. So this is oops, log. This is when we code it in this way, and this is a model when we coded it in this way. Okay. Okay, folks. Now this ends our exercise on logistic regression. Hopefully, this gives you a better idea. But make sure the x is in the range of minus infinity to infinity, and now we convert the probability into the log odds. So that this goes to minus infinity to infinity. In this way, we can set up the logistic regression model. We cannot use, this is not a good model, this is not a good model, although you can do that, but this is not a good model. So that's why in logistic regression, we are trying to model the probability to get either 0 or 1. And at the same time, we discussed the range of odds and the log odds and the p, the probabilities in the range of 0 and 1. So this, I think through this exercise, I designed the x variable to be discrete, 0 and 1, so that you know how to calculate, estimate the parameters. So make sure you this is x equals to 1, and you have probability tipping, and then probability not tipping, right? And the x equals to 0, probability tipping, not tipping. And then you've got odds, log odds. So in this way, you do the modeling and estimate model. And because the way I coded, and I try to make it very easy to estimate those parameters, but it can be extended to x to all the real numbers. But basically, more importantly, let's understand the way why we need to transform the p into the log odds for the modeling. Okay, so this is the end of this lecture.